Now let's do some examples that involve the definition of a definite integral. Okay? Now the first example says express the limit. So here they give us a limit as n goes to infinity of the sum of I equals 1 to n of f of x sub I, or actual function, is equal to e to the x sub I divided by 1 plus x sub I delta x. Okay, so they give us a limit, and what they want us to do is express this limit as a definite integral on the interval that they give. The first interval that they give for this problem is 0 to 1. Okay, so they tell us what your a is. There's your a. Right there, there's your b. So I could write this this limit of a sum as the integral from 0 to 1 of some function. Now I need to find the function that goes right here, okay? The function that goes right here is just this piece right there without the x sub i's. Instead of x sub i's, you're going to write x's. So it's e to the x divided by 1 plus x, and then delta x turns to a dx. That's all you have to do, okay? So instead of writing it as a limit, you wrote it as an integral, okay? That's very much like, it's very analogous. This is the limit definition of a derivative. Instead of writing it as a limit, we wrote it as a derivative. Instead of writing it as a limit, we wrote it as an integral. Okay? Very analogous ideas. Alright, so the next problem is very similar. It's express the limit as a integral on the specified interval. So all this right here is pretty standard when doing these limits. Limit as n goes to infinity, the sum from I equals 1 to infinity. You got a delta x over there. This is from 2 to 7. Now we're going to use this example in a little bit to talk about another example. We're actually going to evaluate this limit in a bit. But it says 5 times x sub I squared minus 4x sub I delta x. Well, writing it as an integral, the lower limit is a, so 2. The upper limit is 7. Okay? And then we just got to put the function there. Okay? 5x squared minus 4x. And then put a dx. So, lower bound, upper bound. We've got our integrand. We've got our function inside of here, and then we've got the variable that we're integrating with respect to, dx. Alright, so as you see, writing the limit as a sum is fairly simple. But what we're going to do now, well, first you should pause the video, go ahead and try that problem that I have for you, and then come back to the video. And now what we're going to do is the next problem. We're actually going to evaluate this integral, okay? To evaluate this integral, what we have to do is evaluate this sum right here. We have to take this limit. We have to find this limit, okay? Now, the problem does say express the integral as a limit of sums. So it's going backwards of what we just did, okay? We took the limit of a sum, expressed it as an integral. Now we're going backwards, taking the integral, expressing it as a sum. Like I said, this first piece is pretty standard, so you just write that, and then you write the functions. Everywhere you see an x, you just replace it with an x sub I. But then usually you have to say what your delta x is. Delta x is b minus a over n. So b minus a, that's 7 minus 2 over n, or 5 over n. So when you're going backwards, don't forget to say what your delta x is, because you're usually not told that. You got to get that from here and here. This is your A. There's your B. Okay, now let's go ahead and evaluate this this integral. This limit, I mean. So x0 is equal to a. Okay, that's our starting point. We're starting at a, which happens to be 2 in this case. Now, we know what our delta x is. I had it up a second ago. We went ahead and found delta x. It's 5 divided by n. Earlier, or in the definition of the integral, to get each xi, that's just a plus I delta x, or in other words, a is equal to 2 plus I times 5 over n. So here's each xi. Now, let's go ahead and look at the definition real quick for a integral. Limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x. I have to take x sub I have to plug it into the function, I have to multiply it by delta x, and when I do all that, I'll be able to take the limit and I'll get an answer, okay? So this is going to get a little messy. Let's see, I'll store my information over here. X sub I is equal to 2 plus 5 over n I. So we still have the limit as n goes to infinity of the sum from I equals 1 to n of 5 times 2 plus 5 over ni squared minus 4 times 2 plus 5 over ni, all times delta x. Delta x is 5 over n. So what I need to do here is I need to take care of this sum right here first. After I take care of that sum, I could evaluate this limit right here. Now, I want to point out that this I right here, it is not in an imaginary number, okay? This is not the square root of -1. This is the index that we're summing over. So I equals 1, we plug in 1. Then we add it 2, we plug in 2. Then we add that answer, we plug in 3, and so on. This is not a complex number. So when you're squaring this, you got to be careful. You're not doing I times I is I squared, which is -1. Do not do that. Instead, what I'm going to do is I'm going to give you what this looks like when you square this out and distribute everything, put together all of your like terms. You get the limit as n goes to infinity. And if you want to work out the details of going from here to what I'm about to put on, go ahead. It's a good exercise. But you get the sum of I equals 1 to n of 60 over n plus 400, or sorry, not 400, 200. Let me see. Wrong line, you do get 400. 400 over ni plus 125 over n squared (625 over n cubed I squared). There we go. I'm missing the squared down here. There we go. That's the one that was supposed to be squared. Alright, so let's take a look at what we have here. We've got the sum of these terms. Now, the sum is over the index I. This doesn't have any i's in it, okay? So, the sum, what you can do is we still have the limit way out here, n goes to infinity, of 60 over n times the sum I equals 1 to n of just 1. Because this has no i's in it, I could move this out front. This is just a constant. Remember what n is. N is how many rectangles am I using for this approximation. That number has to be fixed. I have to set that number, okay? N could be 17. And then that would be 17, that would be 17. 60 over 17 is just a number, okay? So I can factor it out. So I got the sum of 1's all the way up to n. Plus, now I move the sum over here, I get 400 over n squared. The sum, I equals 1 to n of I, plus 625 over n cubed of the sum, I is equal to 1 to n of I squared. Oh, need a bracket there. So all I did was distribute the sum to each piece and factor out any constants that there were. Alright, so I need some more space. I'm going to leave the bottom expression because what we're going to do is we're going to look at these sums right here. Right there, and right there, and see what they're equal to. We actually don't need anything else. Alright, so we still have the limit as n goes to infinity of 60 over n times, now what this sum is doing, this is not an I, this is just a 1. So it's adding 1 plus 1 plus 1 plus 1 n times. 1 plus 1 plus 1 plus 1 n times is n. I'll save the canceling for the next step. I see the n and the n will cancel. Plus 400 over n squared times, now the sum from I equals 1 to n of I. So if I plug in 1, you get 1. The sum of, so plus, I plug in 2, you get 2. So 1 plus 2, you plug in 3, you get 3. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, so on and so on, all the way up to n. Like if n was 10, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 is 55. Okay? So, there's a formula for this, and I would refer to page 381. Okay? They give you the formula for these. Now, this is how you had to calculate these limits. You had to have formulas for these things. If you didn't have a formula for it, it was really difficult, but we're going to get around that difficulty of doing these limits and going through this tedious work in the next section. But if you look at page 381, this is equal to n plus 1, n times n plus 1 over 2. Again, some things simplify there. We're going to wait. Plus 625 over n cubed times... Now, if you look in the book, there's also a formula for the sum of the squares. 1 plus 4 plus 9 plus 16 plus 25, so on and so on. There's a formula for that. Let's see, I have it written down. Give me a second. N plus 1 times 2n plus 1 divided by 6. Okay, so put a bracket there. Now let's go ahead and cancel and see what we have left over, and then we'll be able to evaluate our limit. So limit as n goes to infinity. Well, n here and n here cancel, so we get 60 plus 400 divided by 2 is 200, and we get n squared plus n. I just distribute that to there, divided by n squared. Plus 625 divided by 6, that doesn't simplify, times I'm missing a piece. 625, there's an n right there, okay? It should be n times n plus 1 times 2n plus 1, okay? So we get this n here times n plus 1, 2n plus 1 divided by n cubed. If you notice, this n cubed and this n can cancel, so this makes a squared right there. We can evaluate the limit right now, okay? Don't need that anymore. Limit as n goes to infinity of 60. Well, this doesn't have any n's in it, so that's just 60. Plus 200 times, if I apply the limit here, limit as n goes to infinity, they both have a coefficient of 1. The powers match, so you take the coefficients out in front of the terms that have the highest powers and divide them. 1 divided by 1 is 1. Plus 625 divided by 6 times, you do the same thing. If you were to multiply this out, the highest power would be n times 2n, which would be 2n squared. There are other terms there, but they're smaller than n squared, so we don't have to worry about them because we're taking the limit as n goes to infinity. You use that same idea that we did over here. The n or the exponents match on the numerator and the denominator. So you take the numbers out in front, the coefficients, and you divide them. 2 divided by 1 is 2. So this could simplify. You get a 3 down here, so you get 60 plus 200 plus 625 over 3, which is equal to 1405 over 3. And this is the exact area underneath the curve. Okay. So here, let's go ahead and write our answer. So the integral from 2 to 7 of 5x to the 5x squared minus 4x dx is equal to 1405 over 3. So the entire area underneath this curve is 1405 over 3. This is an exact number, okay? As you can see, the limiting process of a definite integral can be cumbersome, especially if you look on page 381, those formulas, they only give you a formula up to a cubic, okay? What if I were to change this to a fourth power? Do we have a formula that gives us the sum from I to the fourth, from I is equal to 1 to n? Do we have a formula for that, okay? If we did, it's probably really long, okay? I would assume it's really long, but there is a better way of finding these integrals, which is exactly what 5.3 is about, okay? Like I said, this problem, I say, is worth seeing at least once, just so you can get an idea of what you're actually doing when you find an integral. You are finding the sum of the areas of an infinite number of rectangles. Okay, now let's go ahead and do another problem. It's on page, page 389. It's number 33, and they give you a graph. Okay, I'm going to roughly sketch this graph for you. Of course, in the book, it's a lot better. 1, 2, 3. 1, 2. From this. Over 1, 2, 3, 1, 2, 3. And then at 7, 4, 5, 6, 7, it is at -1, -2, -3, -1, -2, -3. And it passes through -5. Or I said -5. And then let's see, it goes 8, 9, and it goes up only 1. goes like that. Alright, so let's go ahead and examine this problem here. They give us, I'm going to do A and B. Again, this is problem 33 on page 389. So they want us to find an integral. Part A says the integral from 0 to 2 of f of x dx. This is our function f. It's probably a piecewise function. We probably could write a piecewise function to this. We're not going to do that. This is how you would go about getting the area graphically. If they just gave you the graph, okay? This is an integral. I told you guys of a way to think of integrals. Derivatives are synonymous to slope. Integrals are synonymous to area, okay? So when you think of an integral, you should be thinking area. So when they tell you to find the integral from 0 to 2, well, starting at 0, right here, going to 2, I need to find this area right here. Now, this area is not hard to find, especially in the graph that they gave you, because it is gridded up really nicely and you can count the grid. So if you notice, let's see, let me see if I can draw this grid pretty nicely. There we go. So since it's gridded up really nicely, it makes counting really easy. If you look at this square right here, what is the area of this square? The area of this square, well, it has a height of 1, it has a length of 1, 1 times 1 is 1. So this is 1. This square is the same size, so that's 1. That's 1. Now you're cutting exactly in the middle of a square, because you go up 1 over 1, up 1 over 1. So this is 1/2, this is 1/2. And now all you have to do, since you found all the areas of all the pieces underneath this curve, you just add them all up. That's exactly what an integral is. You're adding up a bunch of areas. Okay? 1 plus 1 plus 1 is 3, plus a half is 1. 3 plus 1 is 4. So this answer is equal to 4. Now B asks us to do the integral from 0 to 5. We already did from 0 up to 2. We found 0 to 2 to be 4. So all we have to do now is, let's go ahead. This is a nice rectangle we could easily find the area of. This right here is a nice triangle we could easily find the area of. So we could do it that way. Find the area of the rectangle, find the area of the triangle, and then add the areas together. But as I said, this is pretty nicely sectioned for you. Actually, right here, you're not going to be able to find that area. It's not cutting exactly in the middle. So since it's not cutting exactly in the middle, you can't get the exact area. Same with this triangle right here. Okay? If you look at the picture, it's better. It's drawn better. Okay? You can easily see that. So let's go ahead and do that idea. Let's go ahead and find the area of this rectangle. If you notice, it has a height of 1, 2, 3, and it has a width of 1. So the area is equal to 3 in that rectangle. This total area over here was 4. So we know at least from 0 to 3, the area is 7. 4 plus 3 is 7. Now this triangle right here, it has a height of 3. It has a width of 2. The area formula for a triangle is 1/2 base times height. So 1/2 times 2 is 1, times 3 is 3. So the area of this triangle right here is also equal to 3. I know the area of this portion from the previous problem. I know the portion from finding this piece, it's a rectangle. I know the area of this one, it was the area of a triangle. So 4 plus 3 plus 3, the area here must equal 10. All right, so now, next problem asks you to do part C, okay? I have you guys try part C, and it's finding the integral from 5 to 7, so 5 to 7. Now, before you go ahead and do that, we need to talk about the area underneath the curve when the curve goes below the x-axis, okay? If you look at all the problems we did, all the Riemann sums, the one we just did, all the curves were above the x-axis on their specified interval, okay? So if I have some curve like that, let's say it goes like that. If I say A to B, when making these rectangles, this, let's say this was x1, we found f of x sub 1. So this rectangle right here would be f of x sub 1 times delta x. Delta x is always positive. It's the distance between the intervals. But f of x1, it's positive here. So the area of this rectangle is positive. But then, let's say we were to make a rectangle over here. So let's say we make our B, we have some function that has some positive part and some negative part. Okay, it goes underneath the x-axis. Now, if we were to make a rectangle here, this point right here would be f of x. I'm just gonna call it xi. This is still delta x, so the area of this rectangle is f x sub I delta x. The form didn't change. It's still the area of the rectangle, but now look, this f of x sub I is a negative value. So when you find the area of this rectangle, it's going to give you a negative area. So when you are finding definite integrals, when the curve is above the x-axis, you're going to have positive area. When the curve is below the x-axis, you're going to have negative area. So to sum this up, the integral from a to b of f of x dx, if I just have some generic curve like that, let's say I let there be b, I let there be a. Let me get different colors for this. The area here and the area here, positive area, right there, right there. But then, down here, we have negative area. So when you find the integral, you're not finding the total area underneath the graph in either below the curve and above the x-axis or above the curve and below the x-axis. You're not finding the total area. We will come to that in section 5.4, the net area. You're finding the area of these pieces added together, A1 plus A2 plus A3. So if I were to give these labels, so this could be A1, this could be A2, this could be A3, so just A1 plus A2 plus A3. A2 just happens to be negative, okay? So, and when you do that problem on 33, you're gonna go below the x-axis. You're finding areas below the x-axis, so therefore your answer should be negative. You should be coming up with negative areas in this case. Now, lastly, we just need to go through the properties of an integral. Just like when we started out with a derivative, we went through the properties of a derivative. So let's see the first property. It says the integral from a to b of a constant is equal to that constant times b minus a. Okay, let's go ahead and see what this looks like. I can draw you a picture of why this is true. So let's see. I am starting to run out of markers. CLC I can usually get markers from CLC for free. Oh, there we go. I'll work on getting better ones. I know they're running out. But let's say this is some constant, c. Remember, y is equal to c. It goes on forever. It's just a horizontal line through c. And if I want to integrate from a to b, well, the height here in this rectangle c, the distance here is just b minus a. If I want to find the area of this rectangle right here, or the integral of c from a to b, well, it's just the height times the width, height times the width. There you go. So that's the first property. The second property says the integral from a to b of f of x plus or minus g of x dx is equal to, now in your book they split this up into a separate property, one for plus, one for minus. I just group them together, plus or minus. What this is saying is a to b of f of x dx plus or minus the integral of from a to b of g of x dx. So this says that I could either add or subtract the functions, then take the integral, or take the integral of each individual function and then add or subtract them. Just like with derivatives, you could take the derivative of the first function, add it to this derivative of the second function, or you could add the two functions together and then take the derivative. See, the third one says that the integral from a to b of c times a function, so c is just the constant. Well, I could factor the c out since it has nothing to do with the function itself. It's just the constant. I could evaluate the integral first, then multiply it by the constant. Or I could take the constant, multiply it by the function, then do the integral. They're both the same thing. Now, here's the idea of splitting up a jump discontinuity. F of x from a to b, or sorry, the integral of f of x from a to b is equal to the integral from a to c of f of x plus, or dx, plus the integral from c to b of f of x dx. So for instance, in our case that we had a jump discontinuity, here would be our a, here would be our c, here would be our b. If we want to find the integral, or in other words, the entire area from a to b, we could split the integral up. We could do this first part from a to c, and then add it to the second part from c to b. Okay? Now this doesn't only work with jump discontinuities. I'm just using jump discontinuities because this is a great display of the property. But you could also do it when there's not a jump discontinuity. You could always break a continuous function up on its domain, find the area of the first piece, find the area of the second piece, add them together, and that'll give you your total area right there. The next property is what we just got done talking about. If the function is greater than 0, if f of x is greater than or equal to 0 on some interval a to b, then the integral from a to b of that function should also be greater than or equal to 0. So if I just have some function, going from A to B? Well, if you recall what we just explained about positive and negative areas, when I find the areas of all these little rectangles, the function values, their heights, are all going to be positive numbers. Since they are all positive numbers, I'm adding up a bunch of positive numbers. That's what the integral does. It adds up a bunch of areas. Adding up a bunch of positive numbers, I definitely should be greater than 0. And then there's a statement exactly about the negative case. So if you are less than or equal to 0 on some interval from A to B, like that, we're going to have a bunch of negative areas for these rectangles. Since we have a bunch of negative areas, oh, there should be an equal to sign here. Since we're adding up a bunch of negative areas, the integral should be negative, or it should be less than or equal to 0. See, the next one says, if a function is bounded between two numbers, so here's big M, some upper bound. We could put little m down here, and our function f never goes above big M, never goes below little m. It is stuck between big M and little m. Well, these are just constant functions. So if I find the area of this constant function, and I find the area of this constant function, since this is the biggest function compared to this graph, I would draw just a giant rectangle. That giant rectangle, definitely the area of that giant rectangle should be bigger than this function area. Just like down here, if I draw a giant rectangle from like here to here, this giant rectangle's area is negative. The negative area should be definitely smaller than any area I could come up with under the graph. And that's all that's saying is little m times b minus a, or sorry, here, m is less than or equal to f of x, which is less than or equal to big M, for every x in our interval a to b. So we pick somewhere a, we pick another spot b. Everywhere in that interval, the area must be between these two values. Just like that. Remember, this is a constant. This is the very first property we went through. The integral of a constant is the constant times b minus a. Same thing here. This is a constant. The very first property we went through is the integral of a constant, which is just a constant times b minus a. So this is a lower bound estimate for the integral. This is an upper bound estimate for the integral. But if the function is always between these two numbers, it never goes below little m, never goes above big M, you know that this area has to be between these two areas. That's what that property is saying. Now we got two more properties. These are very, very simple properties to understand. The integral, let's see, the first one is integral from a to b of f of x dx is equal to negative integral b to a f of x dx. What this is saying is that if you switch the limits of integration, all it does is produce a negative out in front of the integral, okay? Because when we do these integrals, we're moving left to right, okay? When we go the other way, we're moving right to left. And in doing so, it causes an extra negative. When you add up all those areas with the rectangles, because you're going the opposite direction, somewhere there's going to be a sign change and everything is going to be negative. So switching the limits of integration produces a negative sign out front. And then the last property, the integral from a to a of f of x dx is equal to 0. I mean, if you were to think about what that would look like, any old graph, from a to a, I start there and end there. Well, that rectangle definitely has a height, but it doesn't have a width. The width is 0. So the area of this rectangle is 0. If I'm adding up all the rectangles and they're all 0, well, I get 0. Okay? So that's the idea of a Riemann sum in the form of a limit. It is a definite integral. That is the definition here. We are talking about definite integrals, and how we find definite integrals is exactly like this. So from a to b of f of x dx, we must compute this limit. Limit as n goes to infinity of sum I equals 1 to n of x sub I star delta x. We saw how to do this in the example for this video. However, that was very tedious. It was very long. There is an easier way of finding the integral. And that is what we're going to encounter in 5.3.